everyone, July 28th. Alright, let's do this. Soup servings. I'm gonna serve some soup. There are two types of soup, type A and type B. Initially, we have n milliliter of each type of soup. There are four kinds of operations. Serve 100 of soup A and 0, 75, 25, 50, 50, 25, 75. When we serve some soup, we give it to someone, and we no longer have it. Each turn, we will choose from the four operations with an equal probability. If the remaining volume of soup is not enough to complete the operation, we will serve as much as possible. We stop once we no longer have some quantity of both. We stop once we no longer have some quantity of both type of soup. That we do not have an operation where 100 of soup B are used. Return the probability. Probability of soup A will be empty first. Damn. Wait, hold on. Not yet. The probability that soup A will be empty first, plus half the probability that A and B become empty at the same time. What in the world? The probability that soup A will be empty first. Stop once we no longer have some quantity of both type of soup. If the remaining volume of soup is not enough, then we still do it. And then we stop. But what if one is empty and the other is not empty? Do we still count? We stop once we no longer have some quantity of both type of soup. Hold on. Let's see the example. If we choose the first two operations, if we choose the first operation, A will empty first. If we choose the second operation, A will empty first. Now, whenever you are empty, that's it. Half the probability that A and B become empty at the same time. Ooh, at the same time. Now I like probability problems.
Top.
Okay. Yeah. Alright, I'm back. So we have 50 and 50. If we choose I mean, each has the same probability as if we do option 1. Then this become minus 50. This is 50. So A empty first. I choose option 2. That's minus 25. 25, A first. Choose option 3. 0, 0, A and B. Choose option 4. That's 25 and a minus 25. B. So, and we stop, right? So the probability that A is, and yeah, the probability that A empty first is 2 out of 4, plus probability that's 1 out of 4, and times this. So that's this plus 1/8. Is that right? 0.5, 0.125. Yes, that's right. But so you have to know the total number of operations, right? So you do 1 round, 2 rounds, 3 rounds. Oh, how are we doing this? Or you can, like, as this one says, if each operation is 1/4, and then this we have 100% plus 100%, and that's it. And then we have this is also 100%, but we have to divide by 2, so it's like this. Each round we have a probability of A would decrease by, maybe we can use expected. Is that expected? Well, operation 1, we can say expected is minus 25, right? Because it's 1/4. B expected is minus 0. Operation 2 is expected minus 75 divided by 4, 18.75. Is that right? Operation 3 is a minus 12.5. And operation 4 minus 6.25, minus 18.75. How would you use that? This is expected, right? So what we want to know is how many different ways of combining this can make it up to 50, right? I don't, how are you gonna reason this? Nah, I don't think so. Maybe we need to find, well, n can be huge. Yeah, each round you pick a 1/4. Each round you pick a 1/4, right? So to first round, if you pick 1 out of 4, second round, you pick 1 out of 4. So the probability is 1 out of 4 times 1 out of 4 times 1 out of 4, right? So basically, how many rounds do you need to get, how many rounds do you need to get A to empty first? And A and B starting is the same, right? Which just means how many rounds, how many different combinations will lead to the sum of whatever is larger than the sum of whatever. How many different combinations? Well, if you think about it, right? If you think about it, excluding 4, no matter how we take, right? Excluding 4, no matter how we take. Okay, let's do this. Excluding 3 and excluding 4, 1 and 2. Now, if I take 1, okay, take a 1 once, then I can take 1, 2, 3, no matter how many times, no matter what combination there is, I will always end up with A empty first because we have something A is taken more than B. Same with 2. Okay? So now the question is how many different ways, right? How many different ways you can do this? Or I can do this. I take 1, okay? I take operation 1. Then, after taking operation 1, we have whatever is remaining. Then we want to say, what are the combinations that can empty A? What are the combinations that can empty A? Then we can say, how many combinations, right? Or like we can take A 2 times, and how many? We take A 3 times, and how many? Yeah, we don't have to worry about B. But then you also have 4. Maybe we can find out because we take operation A, okay, and then I can take operation 1, 2, 3. Doesn't matter however many times I want, as long as it fits, right? As long as it fits. So what? Hold on. Let's do the second example. Just kind of get a feeling for it. Second example is 100 and 100, right? If we take option A, we're left with 0, 100. So that's done. Okay. If we take option 2, we're left with 25, 75. Okay. And then we can take option 1, then we left 0, 75. Very good. Or we can take option 2, then we're left with 75, right? So option 2 is also good, right? We can take option 3, is also good. Because we take this, we can take anyone, but we cannot take option 4, right? No, we cannot. If we take option 3, that will end at 50-50, right? Then we can take option 1, we're good. Take option 2, we're good. We cannot take option 3. So these are all the possibilities, right? So what we have is, we have one step, okay? This is, hold on. So we have this plus, we have 2 steps, and then we have 3 different ways. And this is also 2 steps, have 2 different ways, okay? And then we have to figure out the equal chance. Well, equal, we say in this case, we can take option 4. That would be equal, right? So equal will be this squared, equal. Or I can take this 50-50, then we take 50-50 again. So we'll do this one again. And the whole thing times this. Is this right? So we have 0.25 plus 0.25 squared times 3 plus 0.25 squared times 2 plus 0.5 times 0.25 squared times 2. No way, it's wrong. What? What did I miss? I can't even get to the 0.71875. Oh, I think I missed. You can take option 3 first. If you take option 3 first, we have 75 and 25. Right? Then you can take option 1. You cannot take option 2. Which means this has to plus another 0.25 squared and plus another 0.25 squared, because 75, 75 we can go down to 0. So that's 0.75. Oh, hold on. I forgot to divide by 5. Jeez. Hold on. Let me see. Well, we got 0. 0.625. 0.71875. Yes. That is correct. But how do we calculate this thing? Man, I have no idea. It could be too many, possibilities. We can say the state, right? This is like the state. But they have so many different states. It can go to 10 to the 9th. How many different states will there be? It's like, it's by 25, 50, 75, 100. It's still going to be like on the order of 10 to the, 10 to the 6th, 7th power. It's not going to be the way. There has to be maybe a mathematical way to think about this. Again, right? So, this is a bad case for this, but we can use this, right? 75, 25. If we do option 2, okay? We do option 2, then we can take any of the other options. Basically, it doesn't really matter. We can take any one of them and they will work, right? And within each one, we can also take any one of them. Any one of them. Okay, how about this? At each one we take, the amount of A more than B, right? Operation 1, the amount of A more than B is 100. Operation 2, the amount of A than B is 50. Operation 3 is 0. Operation 4 is minus 50. So the question is, right? The question is, how many combinations of these, okay, will lead to a total sum is positive, right? How many can we lead to a total with positive? How many can we lead to a total is positive? But also, a total has to be just bigger than 10 to the 9th. Ten to the 9th. Maybe we can think about maybe when they reach at the same time, right? If you think about all the possibility, they can reach at the same time. And because that seems to be an easier problem to solve. If we figure out what are the different combinations that allow them to be reach at the same time. Okay. Then we can say along the way, at any point, we can swap it with one of the others. Right? At any point, we can swap it with, one of the others. But I mean, others means 1 and 2. We can swap it, and once we swap, that is going to be. But does that make sense? I mean, in this case, in the 100 case, I probably don't even need to do 100 case. What are the even case? Well, the even case is 100, right? So you either do OP3, it's OP3 all the way down, or you do an OP2, OP4. Right? Or OP4, OP2, right? OP2, OP4, OP4, OP2, and you just alternating. Yeah, you need to do OP4, OP2, or OP2, OP4, and see if it's, so that's 100. And if it's not enough, you can also add more OP3 to it. So in this case, it's just OP3, OP3, OP2, OP4, right? So there's 3 possibilities, right? 3 ways. So now we have these 3 ways. We know we do this, we'll reduce it down. So that means at any point, if we swap, right? We swap OP3 with any of the others, 1 or 2, then we'll be good. So we can swap OP3 at this side, we can swap OP3 at this side. So let's say OP3, we can go OP1, OP2, or OP1, OP2, OP3. Okay, we can do OP2. Now OP4, we just need to swap. OP4 can be swapped by all 3 of them, so this can be swapped by 3. But OP2 can only be swapped by the things bigger than you, because otherwise it might not work. So OP4 can only swap by OP1. Okay. Okay. Then what? Then you also have by OP1, OP2, it doesn't involve OP3 and OP4. So we say if we have OP1 start, you can only do 1 or 2. So OP1 is just, that's it. Or you can do OP2. When you have OP2 start, then we don't do OP3 because we consider 3 and 4. So we start from OP2, and then you only get OP1. So we can do OP2, can do OP2, OP2, or we can do OP1. All right, is that all the possibilities? So we have squared. We have 1, 2, 3, 4, 5, 6. I have 6 of them. Triple. I have 1 of them. No. All of them count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them. Plus 1 is this. And this is basically just squared times 3 and times this. Does this one work? Three divided by 2. 0.25 squared times 10 plus 0.25. Nope. Nope. These two are right. OP1, OP3, these are also right. OP2 starts. OP2. Oh, OP2, you cannot do OP4. So OP4, we swap OP4 with 1, 2, 3. Oh, 1, 2, 3. I already handled this one. So this is not. Oh, and OP1, OP3 doesn't really work. I don't feel like, because if the chain is long, you swap something in between, it's not gonna work because you don't know how long the chain is gonna be. That's the difficulty. You don't know how long the chain is gonna be. Yeah, the thing is, we know the chain from we can swap at the end. That will always work. And then the one in front. And still doesn't feel right. Or we can just say, if the first operation takes operation 1, right? Then I can take any combination of 2 and 3 and 1, any combination of 1, 2, 3, right? It doesn't really matter. They're all gonna work. And if we take operation 4, we just need to take another operation 2. So 4, 2 has to be in pairs. Okay? But the question is still, how many rounds can we do this? So basically, let's say given a value, given a k, which is the remaining soup type A, and I have 100, 75, 50, and 75 and 25 basically is 100. So these are the, 50 is also 100. Yeah, 50 is not really 100. We can do 50, 50. 25, 75, we just have to pair them, okay? So it's also 75 plus 25. So we have these four kind of, we can combine however we want. So the question is, how many different ways can we reduce this k to 0? How many different ways? Well, we can do k divided by 10, by 100. Okay, k divided by 100, we can know how many different ways. Just keep taking this, or keep taking this, or keep taking 50 by plus 50. That's not really, you know. Because they could put together a lot of different. Uh, 100, 175. I'll take 75. I'll take 50. Okay. But then they can combine. They can. I can take a 100, right? And then I can take a 75. Oh, still no idea. Or maybe we can ask. We want to reduce k, right, down to 0. Can we take one step? That we can do. Can we take 2 steps? Can we take 3 steps? So all the way down, we will have the smallest steps we need to take. Okay? So from there, right, like let's say 5 steps, we have to take 5 steps minimum to reduce it down. Okay? So if we have 5 steps, okay, then we can ask, how about 6 steps? Can we take it down in 6 steps? Let's say we have 5 times 5 is larger than k, larger than k, and then 75 times a value, I don't know, just 500. How about 480? Let's try 480 divided by 75. We'll take 7 to be larger equal to 480. 480. Okay. and 50 need to times 10, right? It's larger equal to 480. Okay, so we have these around. So take 75 all by itself, take 50 all by itself. These how many we have to take to get to 480. So now we can, you know, maybe we can swap some stuff in and out. What do we say? 100 take 5. So I have 100, 100, 100, 100, 100, right? We'll take 5 times. So maybe a 100 can be swapped by a 75. Well, cannot be swapped by 175. We need to see if we can swap by 175. So with 400, 475 is not enough. So 100 has to be swapped by 275. So we can swap them. Right, we can get 275s, and they can be any place. Yeah, it doesn't really matter. It's just it can be swapped by 275s. It doesn't really matter when the 75 takes place. That's not the issue. We just know that it's possible. Oh, we do need to know. We do need to know. But you don't want to swap by 3, right? So you can say you can swap by 2 75s. Or you can swap, let's say, 200, right? You swap 200 by however many, 75. You swap 3, you swap 4, you swap 5, all by 75. I still no idea. I'm gonna look at the hints. Oh my god, there's no hints. DP, really? You can do DP on this? 10 to the 9, you can do DP with 10 to the 9? Oh god. I have no clue. What type of DP should we do? Well, I mean, in my mind, the DP we shall do if, yeah. Okay, if we want to do DP, I would say DP just A and B. Give me the probability. Because that's what we want to find is DP and N, right? This is the answer. So to find DP and N, we say we need to find DP N minus 100 and the probability of that. And we do to get a 4, right? So this probability of that, probability of that, and probability of that, right? We need a probability, this, and then plus probability of we probably split them up, right? This is to calculate the probability of A reach the end, and then we have also another probability with, oh really, oh my god, I think it's gonna time out. Surely it's gonna time out. She's gonna calculate it. Ten to the 9th. 10 million times. That's not happening. What? Or maybe we can do A and B. If A is larger than B, if A is larger than B, and then we go back to the same problem we have, right? We have no idea. Yep, no idea. It's dp multiple of 25. 25 as one serving in terms of servings operation. 4 servings, 3 servings. N milliliter of soup is full serving plus this. After 19 servings, 18 full servings plus 1 more. Okay, let's stop here. Servants. Well, I didn't think about servants. But still, you take 25 and you have so many servants. Yeah, let's say to get it down, you need 100 servants. And in here, you need 4 servants, right? 4 servants. And each operation, right? Operation 1, you can say is 4 servants. 3, 2, 1. 0, 1, 2, 3 servants. And then what? Let's say in total we need to find 4 servants on one side. So just different combination to get to 4. It's the same. Like right now, it's still the same idea I had. Alright, keep going. I don't like bottom up. Time complexity 01. What the hell? Wait. Problem when we start with I servants of soup A and J servants of soup B. Yes, okay, that's fine. Consider the base case. That's just servants. Well, you don't need servants. You can even just do how much left, right? This is just how much left. Doesn't matter. This means we ran out of soup A, but the probability of soup A is empty first is 1. This is the value. Yes. But how many do we have in dp0j? And this is 0. Both types ran out. Since the answer includes probability, we could consider. Okay, I agree. At each state with this, we have 4 options. Each with equal probability, yes. If we choose the first operation, we'll decrease the amount of soup A by 4 servings. After that, will be in the... That's correct. That's correct. That's correct. Yeah, this should be maximum as well. Oh, I guess because it's larger than 0. Okay. Yes. That's exactly what we have. Yes. The number of state is OM squared options for I and OM options for J. I don't understand why OM for J. Why options for I? Should be in total is OM squared. Oh, I think this is not minus, is this, which explain is OM for I, OM for J. Okay, so this is, yeah, we got stuck here. But for small m, the solution works fast enough. How DPM depends on m. Where the values are with 5 digits after the decimal point. Oh, you gotta be kidding me. You gotta be kidding me. Oh, whoa! Oh, holy crap. Limit, right? Example of a fair coin. The coin can show either heads or tails. Yes, after 10 tosses. Equal number of heads and tails. However, the actual scenario can deviate. Yes, the probability of getting 5. Of getting 4 or 6. The probability of the number of heads falling outside the range of 4 is this. Fewer than 4 heads or more than 6 heads is significant. What if we toss 30? Oh, this is the bell curve, right? This is the bell curve. This is in the middle. When 18 heads. This is the bell curve. 20%. 300 tosses in the range. Yes. As the number of tosses increases, the distribution of the number of heads becomes more and more concentrated around it. Yeah, that's... The more time we toss, the more likely the number of heads will be. Okay. The law of large numbers, yes. The result tend toward expected value. Okay, the four operations there's expected, right? The expected number of servants is this for A and this for B. After completing these operations, the average number of serving is M for A and this for B. So in other words, after this, soup B has on average, yes, well, soup A is already empty. The average scenario, soup A is depleted first, yes. When M is small, there's no really probability that actual number will be, yes. As M grows larger, its probability diminishes. I think that is the intuition. That is the intuition. You can use DP just to find the values when M is small. But when it gets bigger, but what is M? We know M. We know M, right? Yes. How the answer to depends on M. And the starts to getting greater. Use an if state to check is greater than 1. Yes, as soon as this becomes greater than this, we return 1. Initialize, okay, calculate. Very good. Very good. Very good. I like it. I mean, it's a new way of thinking, right? It's a new way of thinking. New way of thinking. But you need to... How do you propose like these problems be solved? Like, let's say you're facing this problem in the interview. What you gonna do? Then I would say the interview is cruel and unusual. Observe. Well, you can do observation, right? Yeah, sure you can. A little bit trick, right? This problem requires some trick. Given the range for n, I immediately rule out dp. But it turns out that we shall examine dp values first, and then we will realize that at certain point dp value becomes 1. when the amount of soup is bigger than a certain threshold. Now the official answer gives a pretty good explanation of why this is the case. But a simple way to think is to find the expected, right? Is to notice that the expected reduction in soup A is bigger than the expected reduction in soup B. Right? Thus, when after sufficient number of operations, soup A will always be emptied, will always be empty ahead of soup B. In other words, when n is big enough, the answer is always 1. However, we don't know what that n is, so we need to use dp, right? Use dp to find the actual probability when n is small. And whenever we get larger than a certain value, right? Whenever it gets big, as soon as dpkk becomes, we'll return 1 as the answer. As we go through, right? And it's small. So as we compute dpn, dpab, right? We split it up to dpa minus 100b, dpa minus 75, b minus 25, dp a minus 50, b minus 50, and dp a minus 25, b minus 50, 75, right? As long as one of them is 1, right, we can guarantee, it is guaranteed dpab is also 1. That is the trick. Edge case. dp 0, 0 shall equal to this probability, right? dp 0, none, 0 shall equal 1. And dp none 0, 0 shall equal to 1. 0. So we can say collection, now func tools, cache, right? Cache it. A, B, turn a float. Okay. If A equal to B equal to 0, return 0.5. A is 0 and B is not equal to 0, return 1. If A is not equal to 0 and B is 0, return 0. Otherwise, OP1 is equal to dp A minus 100 B, right, maximum, if OP1 is OP1 minus 10 to the eta is equal to 10 to the minus 5. So if this minus eta if this is larger or equal to 1 minus eta, this is the error tolerance in online judge. Right, so if this is larger, wait, no, hold on. Yeah, basically this 1 minus this is smaller than eta. I wish I did this. 1 minus OP1 is smaller, equal to eta. Then we return 1. OP2 is dp max 0, A minus 75, max B 0, B minus 25. Right, again, if 1 minus OP2, return 1. OP3, max 0, A minus 25, 0, B minus 75. If 1 minus OP3 smaller or equal to eta, return 1. OP4, so OP4, if this one minus you forgot 50. Okay, otherwise, then we return 0.25 times OP1 plus OP2 plus OP3 plus OP4. Or we can do it, maybe we can do this for OP in generator. I think this is a generator. Not 100% sure, but let's try this. I remember this is a generator. Well, if we can pass, that means it is a generator. Oh, you don't have to. We can just say next A, next B. Alright? So we can just do this, right? Then this, then this, then this. Oh yeah. We have next A, next B. Then we say OP equal to BP next A, next B. Right? If 1 minus OP is smaller or equal to eta, then we return 1. Otherwise, res equal to 0. Res plus equal to 0.25 times OP. Right, and then we'll return res. So we're just going to return dp and n. Is right? I don't understand. It is not right. I mean, I didn't even put everything there. Oh, I forgot one. $75. 0 B minus 25. Nope. It's not correct. What if we don't do this? This one, right? Interesting. Why? understand. Interesting. Okay, NA and B. 1.5. 1.5. Oh, shoot. Wait, that should be 0. NA is 0, NB is... How is these two the same? Oh, my bad. 2575. Oh. Oh, just make a small mistake. I made a small mistake. Yep. Small mistake. Typo mistake. There we go. Okay. And we can try, 10 to the... Holy crap. This is not right. Or it has to be all of them. Is... Wait, that's not... It's not right, huh? Top down is not working. From 1 to K. k from 1 to m. 1 to k. Oh, compute. Hold on. I think it's we have to compute everything, right? We have to compute everything, but at a certain point, if we encounter a 1. Oh, you're talking about like top down is not gonna work on this one. Top down. Why top down is not working? Because top down, you're trying to find that. Then you're trying to find this. You will. Yeah, top down doesn't work. It has to be bottom up. Holy shit. This has to be bottom up. Because top down, you will create all the states, right? Create all the states. Oh well, I mean, probably can do what I'm thinking is you probably shall do for I in range 1 to n. In range n. Okay. We do DPI. If dp ii is -1 and smaller or equal to eta, return 1. Otherwise, return this. Still not right. No, I think it's 1 minus eta. I think this one might be right. Yeah, this one's right. I think I understand now. And it's all saved. Once we have reached the once I is big enough to to get to 1, no need to continue computation, continue the DP. And it's all remembered. It's remembered by DP. It's a tough one. Don't time out. Jesus. Too many combinations, so, oh shoot. How would this help? I'm not sure. Hold on. Let's not make a rush. Seems like directly handling the volume, the soup volume, is not working. We might have to use the official solutions ideal of dealing with portions of 25 milliliter. Maybe we just, there are more states this way? I don't know. Really don't know. There is more states if you think about it. There is more states. Hold on, let me just try. Use portions as suggested by the official solution. Operation 1 has 4 portions on A and 0 portions on B. Operation 2 has 3 portions on A and 1 portion on this. And operation 3 has 2 portions and 2 portions. Operation 4 has 1 portion and 3 portions. So max portion shall equal to n divided by math.ceiling, n and 25. The same, and then this is the same, then this is going to be minus 4 minus 3, then yeah, we can just do b minus 1, and this is minus 2 minus 1. Okay. And it's going to be max portion. Max portion and max portion. Probably have to be plus 1. Wait, hold on. How do you do math dot ceiling? Oh, something divided by something. My bad. So these two is right. Let's see if it's better. 2, 1, 2, 4. Oh, it is much faster. Fewer states. I don't know. Maybe it is fewer states. It is fewer states. It is fewer states. Well, at least you reduce the states by a quarter. It is fewer states. Much fewer states than using the soup as is. Okay, that'll be it. Well, it's a tough one. I'll see you guys tomorrow.